at R equal infinity. If I am 1 meter away, what is the electric potential?
Zero, because R is infinity.
No, that's establishing, in order to, we need to establish where what the constant is.
Okay.
This allows us to establish the constant at is 0.
Okay.
So plug and chug. I have 9 times 10 to the 9th times my charge, 4 times 10 to the negative 9th, divided by R. Preferably without a calculator, but some of you,
Oh,
you can stop anytime.
right. It's over infinity.
36.
Yep, there we go. So my potential there is 36 volts. If I go an additional meter, what's my electric potential?
70T. 70T.
That you're dividing by the distance.
Oh. So it would be 18.
If I go another meter,
I think you're right.
sorry. I've heard several people say things, but not what they've actually said.
It should
12
be,
volts.
sorry, go
Sorry?
ahead.
12 volts.
Yeah, 12. I'm 3 meters away, so divide by 3. And we'll do one more. If I go another meter out, so now I'm divided by 4.
9 volts.
9.
All right. After that, we get into those pesky decimals. So I've got various electric potentials that are decreasing the farther out I go, which makes sense because as R gets bigger, this is a positive number, then as R gets bigger, the fraction gets smaller. If I put a positive charge here, positive charge is going to move to the lower electric potential. If I put a negative charge here, negative charges go to the higher electric potential, or they want to. So, let's see if that still works if that's a negative charge there. So if this is negative 4 nanocoulombs, then 1 meter away, this is negative 36 volts, negative 18 volts, negative 12 volts, negative 9 volts. If I put a positive charge here, I made the claim before that positive charges want to move to a lower electric potential, and indeed, it would move to a lower electric potential. A negative charge wants to move to a higher electric potential, and so it indeed would move to a higher electric potential. I know it's going to be repelled by that, but now we can justify it using the electric potential. So we have 4 ways of explaining the exact same thing.
Does the negative move towards the higher electric potential because it wants to satisfy, it needs a positive electric potential to satisfy being, because obviously they're always wanting to try to become neutral.
I don't know I'm not sure I would take it that far. I've always approached this in the past as less of a need of the charge and more of a after the fact justification. But I guess if I had to, Ben Franklin is the one who set up the conventions that then got adopted and now are used. He pictured the electricity or current as like a river that it flows downhill. And so all of the conventions that he set up were still based upon this idea of something flowing down. And so if you consider, they had no idea if there were negative charges moving or positive charges flowing. It was just assumed it's positive charges flowing. it was set up so that positive charges flow downhill. That's sort of where it's coming from. Right, other questions up to here before we actually talk about what voltage is? All right. Do this. Let's say that's whatever. I've got some systems set up that's 1 volt, 2 volts, 3 volts, 4 volts. If I'm here, actually let's start the charge here, 3. If I'm 3 and this charge moves from 3 volts to 2 volts, first off, if that charge started at rest, is that a negative charge or a positive charge?
Positive charge.
Okay. What is the change in the electric potential?
1 volt.
Ooh. Unless I missed something.
-1.
Yes. Final minus initial. 2 minus 3. -1 volt. If I started at 3 and I went to the -1.
-2.
If I start at the 3 and it starts doing this strange path right here, and ends at the 1, what's my change in potential?
2. -2.
Still -2. It's path independent. So as it goes to 3 to -1, it is -2 volts. This is the electric potential difference. Something for at least some contrast there. Electric potential difference, which is also known as voltage. So electric potential and voltage are related to each other, but they're not exactly the same thing. Except some textbooks play a little fast and loose with it, and they go through the following justification. Although the textbooks that do it, I don't think ever really justify it, they just start doing it. My voltage is delta V. That's going to be V final minus V initial. Here's the rationale for textbook. I can't remember if your textbook does it or not. My formula for electric potential always has this constant, which means I can establish 0 wherever I want. I can make that constant anything just to make it convenient. So they say that the constant be such that V initial is 0. Therefore, my delta V becomes my final electric potential minus 0. Now I'm only dealing with one electric potential, therefore my change in electric potential is equal to whatever my potential is at some spot. This is the rationale for doing it. In class, I will try not to do that, because there are times in which we really need to be, I need to make sure that you understand we're talking about voltage or potential difference, and times when we're actually talking about just potential. And so I do not want to use them interchangeably. But that's the rationale. Same thing that we did, I had no problem with it with time. The fact that oftentimes I just, instead of writing delta T, I just write T. The same reasoning. Or if you're using displacement and position interchangeably, that's because you established your starting point to be 0. All right, now, I have my 1 volt here, I have my 3 volts here. If I have an object moving from 3 volts to 1 volt, obviously there's a change in potential. There's also a change in potential energy. So just as The electric field was the force divided by some test charge. So that'd be the electric field, because of 1 is the force on 2 from 1 divided by the charge of 2. Change in potential energy divided by whatever charge you're getting rid of is equal to delta V. Or down here, that my change in potential energy is just whatever charge that is moving times delta V. We established that this was a positive charge before, because it's going to the lower potential. My delta V is negative, my charge is positive, so my change in potential energy is negative. So we lost potential energy. If I put a particle there and it moved to here, we lost potential energy, therefore gained kinetic energy. So it all fit together. So if I'm going from one potential to another potential, there is energy involved. Work has to be done of some sort. However, if I have 4 volts here, and this is an equipotential line, in other words, a line where all the potentials are the same, if I have a particle moving from here to here, there's no change in the electric potential, there's no change in potential energy. It takes absolutely no work to do that. In theory, if I had an equipotential line and a particle sitting on it, I can just tap that particle just slightly and it can move anywhere along that line forever. So that was what you were finding in the lab on Wednesday, is you were finding the points where they had the equal potential so that you could draw an equipotential line. And the other bit, we'll take this simple example and then sort of expand it and then generalize it. If I have a point charge here, Q, Q is a constant for this problem, K is a constant because it's a constant, R, excuse me, choking on my words. R is a variable, but for any value of R, it's the same value for the electric potential. So my equipotential lines around a point is a circle, or a sphere, depends on how many dimensions you want to go. These are my equipotential lines here. Also, I can draw my electric field lines. If we assume Q is a positive charge, the electric field lines go like that. Notice what's true in this particular case is that my electric field is perpendicular to my equipotential line. And that is the way it should be. The electric field is perpendicular to the equipotential line. So if I had some configuration of, let's say I have, those are equipotential lines, and actually they should never cross. So 1 volt, 3 volts, 5 volts. If I was drawing an electric field line on here, well, at this point, it's going to cross perpendicular to it. It's going to have to start bending because I need to go in at some angle like that, so maybe something like this. Oh, that didn't quite hit right. It's going to have to curve there too. So the electric field line will look something like that. Actually, there is a mistake here. Goes the other way. So when we're looking at the relationship here, first off, electric field is perpendicular to the equipotential line. So when you're drawing your electric field lines, please make sure it is perpendicular. When I grade that lab, I look at your sheet there and I look at your equipotential lines, and then I look to make sure that your electric field lines actually are perpendicular at the points where they intersect. The direction of the electric field, well, I know as I get farther from a positive charge, it goes down, but the potential goes down. And I know electric field lines go away from positive charges, and so electric field goes points to the lower electric potential. Because when you put the probes on the negative and positive, you had 12 volts. And then as you got closer and closer, as you moved the one that was on the positive tack, as you moved it closer and closer, you started getting lower and lower potentials, which is also the direction of the electric field lines. And class ended 9 minutes ago. Oh, wait, no, 9? 4 minutes ago. Sorry. Flashback to 5 years ago. Hopefully that's enough to help you on the lab. The analysis piece where you're finding the electric field at a particular point. There is a video that I think is cleverly labeled under videos to watch. It's cleverly labeled like, this will help on the lab too. TOO. So you might want to check that one out. I just put the link in. I think I put it on yours. I could have put it on the other one, on the 252 version. But there, I think there's a link for 151 saying if you want help with the analysis piece, here's the link. Something clever like that.